Okay, my presentation is visible to everyone.
Sorry, it's visible.
Okay, thank you. Thank you so much for confirmation. Yeah. So today is class fifth. Okay, 8 January 2024. So unit number first. Still we are in the unit number four. First. So hopefully today we will complete this unit. That is introduction to electric drives. Okay. So this is my second slide. Is it visible to everyone? Second slide. Yes, Madhusudan, just confirm me. Is it visible
Sorry.
to? Okay, thank you,
Sorry.
thank you so much. Okay, so in the previous class, we discussed the components of the load torque and classification of the load torque. Also, we discussed that is a previous topic from the lecture number third. Okay, so is there any confusion, any doubts from the previous class? So that is the components of the load torques and classification of the load torque. Any confusion, any doubts from the previous class? Also in the previous class, we discussed the how to calculate the moment of inertia. Okay, so one of the student told to me, so they have a confusion on the moment of inertia. So in the previous class, we also discussed the retardation test to calculate the moment of inertia. So if you have any confusion, any query from the previous class, then let me know. If you don't have any query, then we will start our next topic. Okay. So if you don't have any query, then we can start our official class. So today we will discuss the time and the energy losses in transient operation. And second topic, that is a steady state stability of electric drive system. Okay. So today we will discuss these two topics. Okay. So we have to calculate the time and energy losses in the transient operation. And we all of you know what is a transient operation and steady state operation, correct? So we can say the dynamic operation as well as the steady state operation, correct? So whenever we can say the dynamic operation and steady state operation, then we can consider like this. So this is maybe the speed, this is maybe the time, and this is maybe the speed. Okay, so we can say we can start the motor like this and then it is a stable like this. So we can say this time period it is your transient response, and this time period it is we can say the stable response, stable otherwise the steady state response. Okay, so during this time period we have to calculate the energy, that is a time and energy losses. Okay, so during this time period we have to calculate the energy losses because your speed response is maybe the fluctuate, otherwise we can say suppose your speed is something like that and after some time it will stable. Okay, so we can say this is your transient response up to this time period. Maybe we can say point number A to point number B. So point number A to point number B, that is your transient response, and point B to point C, we can say it is your steady state response. So in the case of steady state response, there is a no energy losses. We can say our motor is rotating at a steady state speed. So there is a no dynamic operation, no transient losses. Okay. So we can say our efficiency is we consider that 100% depend on your system. Okay. But what about in the transient operation? Otherwise, what about in the dynamic operation? So that we have to calculate the time and energy losses in transient operation. Once we understand the transient operation, then finally we have to check the steady state stability of the electric drives. Okay, done. So let's see how we can calculate the energy losses in the transient operation. Okay, so we already discussed the four quadrant operation. That is your forward motoring, forward braking, reverse motoring, and the reverse braking. Correct. So whenever we can say the four quadrant operation of electric drive, it means it is a transient operation, correct? Because we can start motor from 0 to the maximum speed. So once we can start our motor at the time equal to 0 second and speed is a 0 rpm, then slowly increase the speed of our drive, correct? Then we can say at the starting, braking, and speed change and speed reversal are the transient operation. Correct? How we can say the transient operation? Transient operation means we can say starting time, because as a starting time it will the jerk. Correct? It will give the jerk. Okay, because of the moment of inertia, because of the controller nature, many parameters are there for the jerking. Correct? Then we can say the braking. Yes, we can say sometimes we have to give the brake. Speed change, sometimes you have to change your speed, you have to increase your speed, you have to decrease your speed. And the speed reversal, sometimes you have to do the speed reversal. So during these four function, it will create the transient operation, correct? So then we can say we have to calculate the transient, we have to calculate the time and energy losses in the transient operation. Okay. So time and energy losses in transient operation can be evaluated by the equation number 6 along with the motor circuit equation. So we all of you know the fundamental torque equation, that is a T, total load torque, equal to J, moment of inertia, upon rate of change of speed, that is a d omega m by dt, plus your total load torque plus B into omega m. So we can say there is a damping function into omega m. Other component, that is a friction, static torque, viscous torque, we can neglect, because magnitude of this friction, piston, and viscous torque, it is a very less compared to the fundamental torque. Okay, so we can neglect this component from the fundamental torque equation, and then we can say our fundamental torque equation is a equation number 6, that's a T equal to J d omega by dt plus TL plus B omega m. Okay, and that friction torque, static torque, viscous torque, we already discussed in the previous class. Okay, so when T and TL are constant or proportional to the speed, okay, so we can say T, this component T and TL, so we can say this is capital TL, both are constant, otherwise it is a proportional to the speed, then we can say equation number 6 will be the first order linear differentiation equation. Why first order? Because here term is a d omega m by dt. So we can say power is a one power only single power. Then we can say the first order equation. Suppose equation is dm by dt square, then we can say the second order equation. Okay, done. So that depend on the power of the omega m, then we can say it is a first order, second order, third order, fourth order equation. Okay, so generally in the drive system we refer the equation in the first order as well as the second order equation. Okay, so just I am talking about the this equation number 6, that is a fundamental torque equation. Okay, suppose that load total torque and the load torque both are equally, otherwise the both are the proportional to the speed, then we can say it is a first order equation. Okay, where T and TL is neither constant nor proportional to speed, then equation will be the non-linear differential equation. Of course, suppose T and TL both are the not equal, correct? Otherwise, that is a not proportional to the speed. Then this equation number 6, that is a non-linear differentiation equation. Once we have a non-linear differentiation equation, then it will difficult task to calculate the remaining parameters. Maybe we have to calculate the omega, maybe we have to calculate the J, maybe we have to calculate the B. Once our equation in the non-linear case, then it will difficult to find out the remaining parameter. Yes, we can calculate the remaining parameter by various method. it could be then be solved numerically by the Ranga-Kutta method. Okay. I think you heard this Ranga-Kutta method in the BTech semester. There is a mathematical subject, maybe the mathematics 1 or mathematics 2. Also, this Ranga-Kutta method in the power system. Okay, maybe you studied this power system subject in the first semester in the MTech. Okay, so Ranga-Kutta method is a very famous. So wherever is a nonlinear equation, so by Ranga-Kutta method we can solve nonlinear equation. Just 1 minute. Somebody want to join the class? Yes. Okay. Yeah. So Uh, yes, so once we have a nonlinear equation, then we can solve by Ranga-Kutta method, and that is a famous method. Normally, people use the to calculate the remaining parameter. Okay, but for this subject, we don't have to solve the nonlinear equation by using the Ranga-Kutta method. Okay, but for your kind information, suppose you have a nonlinear equation, then we can use the Ranga-Kutta method. Okay. Now, how we can find out the energy losses in the transient operation? Okay, so we already see the fundamental torque equation. Then we can see the first order linear equation. Suppose T equal to TL. Suppose T directly proportional to the speed. Suppose T and TL both are the not equal and not proportional to the speed. Then it is a non-linear equation, and that we can calculate by the Ranga-Kutta method. Yes. Now slide number 5. Okay. Slide number 5, that is a figure number 6. You can see the figure number 6. Okay. Figure number 6. That is a calculation of the time during the transient operation. Okay. So as I said, transient operation is a slowly increase the speed, correct? And once the increase the speed and once the motor reach in the steady state condition, during that time period we have to calculate the energy, correct? So you can see, suppose speed is starting, maybe here is a 10 rpm. Okay, so you can see slowly speed is increasing. Okay, slowly speed is increasing, and once the magnitude is a fixed, so now you can see from here is magnitude is a fixed. Okay, so you can see the variation in the speed from this time period to this time period. So maybe we can say that this is omega m1, and this time period is omega m2, and this is your omega me. Okay, so on the x-axis that is a speed response, on the y-axis that is your moment of inertia plus load torque. Okay, on the y-axis, then we can say your energy losses, in which part we can say your energy losses. So that is a from omega m1 to omega m2. So we can say yes, we have to calculate the energy losses in this time period. Okay, done. So you can see this equation on the y-axis equation is a j upon t omega m minus TL into omega m. Just 1 minute. Somebody want to join the class. Correct? So we can say there is a J upon total torque into omega m minus TL into omega m. Okay, so that is on the y-axis. And how we can calculate this thing? So from the fundamental torque equation, correct? So this is your graph. That is by speed. That is on the y-axis. That is a moment of inertia plus the load component, and on the x-axis that is your speed. Okay. So we can say for the any of the above mentioned transient, the final speed is an equilibrium speed. Okay. Above mentioned transient means maybe your speed is your increasing, reversing speed. Okay. So above mentioned transient means starting, braking, and the changing of the speed, otherwise the speed reversal. Okay, so this is your transient operation. Okay, so equilibrium speed operation. Okay, so theoretical we can say theoretically transient are the over the infinite time. Yes, theoretically we can say that our practical application we can say motor is not stable. It will give the error. Maybe sometimes it's a 1500 rpm, maybe sometimes it's a 1480 rpm. So we can say the 20% error. Okay, but we can say theoretically transient as an infinitive time, which is not so in the practical. Correct? Practical that is not possible, but theoretically we can consider. Correct? To resolve this thing, time and energy losses in the transient operation is considered to be the over than 95% change in the speed has taken the place. Okay. So this 95% we can consider motor is now stable condition. Now transient period is over. Correct. So generally we can consider in the practical case, but in the theoretical case we can say now motor is a steady state condition and their losses is a negligible. But practical case that is not possible. But for the simplicity, for the simple calculation, for the simple analysis, we can say transient operation can be considered to be over when the 95% changing in the speed. Okay. For example, let's we can take one example. When the speed change from omega m1 to equilibrium speed, that is omega me. So omega m1 is here from omega me. So from this speed to this speed, okay, from this speed to this speed, just I am changing the color of this pen. Yeah, from omega 1, omega m1 to omega me. Okay, when the speed change from omega m1 to omega me, the time taken for the speed to change from me1 omega m1 to omega m1 plus 0.95% into omega e into omega m1. So this is a simple mathematical, correct? So we have to calculate the time period. So from this time period to this time period, correct? So this is a simple time period calculation, correct? Okay, done.
So that how that J by T omega m minus TL omega m, that how to obtain this from dynamic equation, sir?
Can you just repeat your question?
So how to obtain that this J divided by T, that y axis from dynamic equation, sir?
Yeah, so this equation is a, so this is your equation, correct? T equal to J d omega by dt plus TL plus B omega m, correct?
Yes, sir.
Okay, okay. So we can say we have to plot the graph, correct? From this is on the x-axis that is omega, and on the y-axis that is your total torque. The torque involved in the moment of inertia and the speed component, correct? So for this case, we can say J, just 1 minute. Yeah, I can derive here also, no issue. So we can say equation is a J divided by T into omega m minus TL into omega m. This equation, correct? So we can say this B omega m we can neglect it. Okay. B omega m, because this is a first order equation. So we can take the derivative. Okay. We can take derivative, and B omega we can neglect it because this is a viscous damping, correct? Damping coefficient, correct? So we can say compared to T and load torque, we can say T and TL. Both are the torque component, and B, that is a damping coefficient. So magnitude of damping coefficient is very, very less compared to the T and TL. So we can neglect it, this component, that is a B, from this equation. So remaining quantity is a T equal to, remaining quantity is a T equal to J d omega m by dt plus TL. So this is the remaining quantity, correct? Okay. Can I take the one new slide? Just 1 minute. Then you will better understanding. Just 1 minute. Yeah. Yes. Yeah. So we have a main equation that is your T equal to J d omega m by dt plus TL plus b omega m. Correct? So we can say T greater than TL greater than b omega m. This is a condition whenever we can say the first order linear equation. Correct? So magnitude of T total torque is more than load torque, and b omega m is a very less. So we can say T and TL compared to T and TL, magnitude of the b omega m is a very less. So magnitude of the b omega m is a very less. So we can say we can neglect the b omega m. Correct? Now remaining term is a t equal to j d omega by dt plus TL. We have only this equation. Now we can say equation number 1. Okay. So now we can say we have to calculate the energy losses, correct, during the transit operation. So what is the transit operation component? D omega by dt, that is your transit operation. So this is your transient operation. Okay. So what is a transit operation? Transit operation component is a d omega by dt. Okay. So we can say T minus TL equal to J d omega m by dt. Correct? Any confusion? Still now any confusion?
No, sir. No, sir, till now.
Okay. Done. So now we can say we have a equation. This is a T minus TL into J d omega by t. Okay. Now we have to calculate the energy for the transit operation. Okay. So we can say for transient operation, because of what? Because of the speed. Correct. So we can say T minus TL, and transient operation because of the speed. So we can say the speed is here, and T d by dt. Sorry, d by dt here. Correct. And y omega m is here because of the transient operation. Then we can say with respect to time, we can say j equal to we can say j divided by omega m t minus tl is equal to dt. Can you write this equation like this? From equation number 1. Correct? Is there any confusion? Okay. Done? Now any confusion?
No, sir.
Okay.
This last line not understood, sir.
Okay. Last line, this one, yeah, this one, this equation.
Is the second last one, sir. Second last.
Second last, correct? So we can say now we have to calculate the energy losses during the transient. So which component is a transient? Transient component is a, just 1 minute, I am changing the color. So transient component is a d omega by dt. Okay. Whatever component changing with respect to time, it will the major components of transient. Correct. So here is transient component is a speed, because speed is changing with respect to time. Correct. Moment of inertia is a constant component. Load torque is a constant component. Total load is a constant component. But only changing component, that is a speed, because speed is changing with respect to time. So we have to calculate the energy while transient operation, correct? So we can say we have to plot the graph with respect to J upon torque and with respect to your omega, that is a speed. Why we have to plot the graph with respect to the torque, with respect to torque and omega? Because that is a transient operation and we have to calculate the energy. Okay. So we can say from equation number 1, we can easily calculate the T minus TL is equal to J d omega by dt. Okay. Any confusion in this equation? Maybe equation number A. Any confusion in equation number A?
Sir, I think we are very close there. We can take dt on the left side, cross multiply, and take t minus tl in the right side bottom. Then by integration of both sides, we can get area, no?
Yes, yes. So that is the second part. So that is the second part.
Sir, I think
Here I mentioned that integration. You can see this is a equation number 8 is a integration. You can see
okay, sir. Okay.
equation number 8 is the integration part. Okay. So now any confusion in this equation? correct? Okay, so now we have to calculate the energy for this area. Okay, so how we can calculate the energy? So just we have to integrate the integration of the limit. So this is a omega m1 to omega m2, because this is simple mathematical concept. So suppose you want to calculate the energy from this area, so what you can do, you can just take the integration from the starting point to the last point. Okay, done. So yes, transient time and energy losses can also be the compute with the satisfactory accuracy using the steady state speed torque and the speed current curve of the motor and speed torque curve of the load. So we can say generally we have a electrical quantity, there is a voltage and current, and we have a mechanical quantity, there is a torque and the speed. Okay. So suppose you want to calculate the energy losses, correct? Energy is what? There is a time into work done, correct? So that is your energy. Okay. So we can take the voltage quantity, current quantity as a electrical quantity. Otherwise, you can take the speed and the torque quantity as a mechanical quantity, and then you can easily calculate the energy, correct? So whatever area you want to cover, that area you can consider, and then you can take the integration. Okay. So this is a because of the mechanical time constant of the drive is usually very large. Okay, compared to the electrical time constant. This is a simple thing. Whenever we can see the mechanical time constant, it is a very high compared to the electrical time constant. Okay. Consequently, electrical transient die down very fast and motor operation can be considered as taken place along the steady state operation. Yes, mechanical time constant is very high, then we can say it will take time to stable operation, but electrical time is very less, then we can say it will take the very quickly in the stable condition, correct? Then we can say equation number 7, that is a simple equation from the fundamental torque equation. We already derived in this slide, okay, that T minus TL into T minus TL into omega M is equal to J d by dt, correct? So same equation here I written in the equation number 7, that dt equal to J d omega M divided by T omega M minus TL into omega M. Okay, so this is a simple thing
Right.
where T
So I
omega
think
M.
that is
Mhm.
so that is a, I think that is not into omega m. That is torque at that speed. I think
Torque.
torque at omega m speed, or torque into omega m.
So this is a torque into omega M. So this is torque into omega M. Denominator, you are saying the denominator?
So see the line just below that, where T omega m and TL omega m indicate that motor and load torques are function. No, sir. Function means not into there.
Okay, okay. In this equation, you are telling this equation?
Yes, sir. Yes, sir.
Hmm. So can you just repeat your statement?
Yes, sir. Just below, just read the line below that
Yeah,
equation.
where T omega M and TL omega M indicate the motor and load torque function of the drive speed omega M. So what you are saying?
I'm saying that T is not multiplying omega m. It is T of omega m. T is a function of omega m.
Yeah, okay, okay. So T is a function of the omega M, correct? T is a function of the omega M. You are saying something like that, correct?
Yes, sir.
T is a function. Obvious, that is a T is a function of the omega M. Obvious, because this torque is a dependent on the your motor, correct? Motor speed. Suppose torque is a changing, then your speed is also changing, correct? Suppose motor is running and you suddenly increase the torque, then it will affect on the speed also. So we can say torque is a function of the speed, as well as we can say your speed is also function of the torque, because both quantities are dependent to each other. Suppose you increase the torque, then it will directly affect on the motor speed, and suppose you decrease the torque, and then it is also dependent on the motor speed, correct? So it is, yes, you are correct, it is a torque is a function of the motor speed. Okay, now any more confusion in this equation number 7? Now it is a last step to calculate the energy. We have to calculate the area. Okay. And how we can calculate the area? So just we have to take the integration. So whatever area you want to cover, suppose this is your graph. Okay. Suppose this is your graph. We can say this graph, and you want to calculate the from 1 to 2 this area. Then you can say, we can say this is omega m and this is a torque. Then we can say we have to calculate the energy from area 1 to area 2. So we can say T equal to 1 to 2, and here is whatever is a function. Okay, so f of x is a whatever is a function. So we can say here in this case f of x is your so we can say f of x is nothing but d omega m by t function of omega m minus tl function of omega m. Correct? So f of x nothing but this function. Okay. So finally we can calculate the time take for the drive the speed to change from the omega m1 to omega m2 is obtained by integration of equation number 7. Okay. So we can just integration and we can take this area. Okay. From equation number 8 can be integrated only if function t omega m and tl omega n are known and are integral form. Then we can calculate this time, and once we know this time, then we can easily calculate the energy losses. Correct? So this is a simple process to calculate the time and energy losses in the transient operation. Now, any confusion? Till now, any confusion from equation number 8? Any confusion? So here we calculate the time. Okay. Now we have to calculate the energy losses. Okay. Yes. Energy losses, that is a WM2 is the equilibrium speed of WME. Okay. The reciprocal of the acceleration will become the infinite at omega me. So what is the omega me? Omega me, you can see omega me is, this is a final speed. Okay, this is omega m1 and this is omega m2. Okay, so we can say when omega m2 is equilibrium speed at omega me, yes, then reciprocal of the acceleration will become the infinite at omega me. Okay, therefore, in this case, transient time is computed by the measuring the area between the speed omega m1 and omega m1 plus 0.5 omega m2 minus omega m1. So this is simple. Whatever area you want to cover, so that area we have to take the time response. Correct? Done? Yeah. So finally, energy dissipate in the motor winding during the transient operation is given by E equal to integration 0 to t, whatever time period you want to cover, into r into I square into dt. Okay, that is equation number 9. And why r into I? Because now we have to calculate the energy losses, and whenever we can say energy losses, then we can consider that is a resistor, winding resistor, and I, that is your current flowing through it. Okay, so that is your energy losses, that is a r into I square into dt. Okay, and that integration from 0 to total time period. Whatever time period you want to cover in the transient operation, that time period you can cover, and you have to consider that is a r that is a motor winding resistor, and I, that is your current flowing through it. And you can see I that is your torque component, because torque is directly proportional to the current, and voltage speed is directly proportional to the voltage. And whenever we can say voltage, then we can say V equal to IR. Okay, so that's why we can say torque is directly proportional to the current and speed is directly proportional to voltage. Then we can say we can calculate the energy E equal to integration of the R into I square into dt. So this is your final equation for
So,
the energy. Yes.
so I think that I square current will also change when your torque will change.
Yes.
Now I should also be a function of omega torque like that.
Yes, of course, because we are doing the integration, correct? we are doing integration 0 to t. Okay, and this time period, we have to cover the time period, correct? Whatever, so suppose your graph is like this. Yeah. Suppose your graph is like this, correct? So this will change with respect to time, correct? This will change with respect to time, correct? So we can say with respect to I square, this dt, so this I that depend on the torque, because torque is directly proportional to the I. So suppose I will change, then torque will change. So torque will change, and torque is also function of the speed, correct? Torque is also function of speed. Then also I will change. So that is a direct relation. Got it?
Yes, sir. Yes, sir.
Yeah. Okay. So we can say, that's why we can say V equal to IR, voltage is dependent on the speed, I is dependent on the current. So suppose your torque will change, then speed is also change. Correct? Because V equal to IR, that is a electrical quantity, and torque and speed, that is a mechanical quantity. But all are dependent to each other. Okay. Now any confused this time and energy losses in the transient operation? Any confusion, any doubts? Yes, student. Okay, good. So now we can start the last topic, that is a steady state stability of that style. Okay. Now I want to discuss this topic on the 2 to 3 minutes from the your side. What is the meaning of steady state stability? Yes, just I want to check your knowledge, how much you remember that is a steady state stability and the transient stability. Then we can start our topic. Yes. Manoj Wagle. Yes, Manoj Wagle. Any idea? What is a steady state stability?
The stability that we can get after the transient response is over. That is when our motor is running in a constant speed or stable speed, sir.
And why we have to analysis the steady state stability? What is the importance in the control system?
Because in a feedback system, we need to know if our motor is running in a constant speed or not, or in our desired speed or not.
So is it necessary to we have to analysis the transient steady state stability?
Yeah, we have to study the steady state stability because sometime in our motor there could be any jerk or anything that may lower our speed, or sometimes the load might
Okay.
increase that will change the speed of the motor. So in order to have that feedback system, I have to analyze the steady state, because according to that we need to change our voltage or current.
Okay. Good. Good. Yes, Saroj Kumar, are you there? Yes, Saroj Kumar. Okay, Samudra Thapa.
Yes, sir.
Yeah. Are you fine?
Yes, sir. Very much. How are you, sir?
Fine, fine. So what is the status of MATLAB?
MATLAB, sir. I am doing, sir.
Doing?
Yes, sir.
Good. Good, good. Yeah. So can you just tell me the transient steady state stability?
Yes, sir. Actually, what Manoj said, sir, I fully support him, sir.
Mm-hmm.
Uh, steady state, steady state stability is the ability of system
Mm-hmm.
to remain in synchronism after facing certain small disturbance.
Mm-hmm. So is it possible without the analysis of steady state stability we can design the controller?
Yes, sir. It might be possible, sir, but we have to do analysis, sir, because we have to know in the future the system will have the ability to withstand certain small disturbance or not. So we have to do analysis first, sir.
Okay. Good, good. Yes, Niroj, are you there? Niroj,
Yes,
Niroj.
sir.
Yeah, good, good. How are you?
Fine, sir.
Fine, good, good. Yeah, so can you just tell me to in which system losses are more in the steady state or transient?
Losses, I think, mm, losses, it can be measured in the time, sir, yeah. So in the steady state, I think the losses is more. In the transient
Okay.
conditions,
Mm-hmm.
we have to design the systems to face that transient state. So the system need to be uh, more robust at the transient state, but loss may be the high in the steady state.
Okay, okay, good try. Here, yes, Asis, what is your comments on that
So he's
question?
correct, sir,
So in
because
the transient,
I think he's correct, sir.
so
Because
in the
in
transient losses is less.
transient time comes for a small time instant, but steady state is continuous.
Okay, so losses is less in the transient, but in the steady state losses is high.
Uh, it depends on.
Okay. Yeah, so it is a depend on the system to system because maybe the transient period is transient period is very less, but it is a magnitude is a very high. Then we can say losses is a high. But suppose that magnitude is a very less, then we can say losses is also less. Correct. So that depends on the situation and depends on the system. We cannot say it's always in the transient condition your losses is very high, and yeah, we can say it is a steady state condition losses is also high. We cannot say like this. It depend on the time duration and depend on the magnitude. Okay, so we cannot say that it is a thumb and rule. So in the transient condition losses is very high, yeah, losses is very less. Okay, got it. So that is a good. So you have a sufficient knowledge on the steady state condition as well as transient condition. So we can start our topic. So that is a steady state stability of the drive. Okay. Yeah. So steady state stability of the drive. So in the equilibrium speed of the motor load system is obtained when motor torque is equal to the load torque. How we can say steady state? We can say the torque load torque equal to motor torque. Then we can say it is a equilibrium speed, otherwise the steady state condition. Correct. So we can say the load torque equal to the motor torque. Okay. Drive will operate steady state at this point, provide its speed of the stable equilibrium condition. Okay, so we can say your speed is something like that, correct? And this is omega m, and this is you can say the torque. Okay, so when we can say T equal to TL, so load torque equal to the motor torque, then we can say the stable operation. Okay. So concept of the steady state stability of the drive has been developed readily evaluate the stability of the equilibrium point from the steady state and steady state speed torque curve. Okay. Thus avoiding the solution of the differential equation to validate the transient operation of the drive. So why we have to analyze the steady state stability? So we can say we can avoid the transient operation, we can avoid the transient analysis. So you can see, so we can avoid the solution of the differential equation to valid for the transient operation. Okay. So once you analysis the steady state stability, then you can say you can avoid the transient analysis. That is a different to find out the solution of the differentiation equation. That is a first order equation. Okay. So once you can see the steady state condition, then you can say now system losses is this much and no need to go again with the transient stability. Okay. So this is a theory part. Yes. So how we can check the stability? So now we have to check. We can say take the graph figure 7, that is a point A is a stable. So how we can say point A is a stable? Any idea? Yes, student. Any idea how we can say the point A is a stable? Anybody give the comments on this? So maybe I can draw here again this graph. So like this line, just 1 minute, and this line. So this is a TL and this is a T, and this is a point A. So this point A is a stable point, yeah, unstable point. Yes, any idea, student? So we can say this is a torque and this is a omega. Any idea how we can define the stable operation, yeah, unstable operation? Yes, any idea? So already in the previous slide we discussed that is a stable operation means load torque equal to the motor torque. Okay, so you can see this is a load torque, this is a load torque, and this is a motor torque. So we can say T equal to TL, then we can say the stable operation. So here is a point A, and this is your TL. Just a minute. This is your TL load torque, and this profile is a motor torque. This profile is a motor torque. So point A is stable or unstable? Can you give your comments on this question? Any idea? Yes, starting from the Assis, what is your comments? Is it stable or unstable? And how?
So the point
Yes,
of
Assis.
intersection, because of T equals to TL, then as you told, it is stable.
So
Uh,
this point is A is a stable or unstable?
A is stable because as that developed torque is increasing, your speed is decreasing, and
Okay.
in the load side, as load torque is increasing, speed is also increasing.
Okay. Correct. So we can discuss. So you can see we have original graph. This is on the y-axis there is omega m, and on the x-axis there is a torque, and profile of the load torque that is a increasing. Profile of load torque it increasing, okay, and profile of the torque motor torque is a decreasing, okay. So intersection, both torque profile intersection at point A, correct, and we have to find out that is a profile, we have to find out that point A is a stable or unstable, correct, and we already know when we can set a stable. So stable means T equal to TL. So is this condition is fulfilled for this graph? Suppose yes, then we can say it is a stable. Suppose no, then we can say it is a not stable. Okay, then you can see, just 1 minute. So you can see at this point, suppose we can consider this point, okay, and same we can say this point, okay. So you can see here is a motor torque is here, okay. So its speed is here is we can say the omega 1, and at this point, at the same point, load torque is also decreased, omega 2, and motor speed is also decreasing. So you can see both quantity proportionally decreasing, correct. So once decrease in the motor torque, then once you increase in the load torque, then both quantity is proportionally dependent and both quantities equally. Then we can say it a stable operation. Correct? Done? So the equilibrium point will be the term as a stable when the operation will be restored to it after the small departure from it is due to the disturbance. Okay. So once you disturb the system, maybe you increase the speed, yeah, maybe you increase the motor torque. Otherwise, you can decrease the load torque. Okay. So proportionally, you have to vary the load torque as well as the motor torque. Okay. So let disturb the cause of reduction of delta omega m. So we can give the disturbance delta omega m. Okay. So delta omega m is nothing but delta omega m is nothing but omega m2 minus omega m1. So it is a just disturbance, small disturbance in the speed. At the new speed, the motor torque is greater than the load torque. Okay, so motor torque is greater than the load torque. So we can say the motor torque is greater than the load torque. Consequently, the motor will accelerate and operation will be restored to the A point. Okay. Similarly, delta A omega m again you increase. Okay. Speed caused by the disturbance will make the load change greater than the motor torque. Okay. Whatever you can do, that is a changing delta omega. Again, you will get the same relation, that is a T equal to TL. Then we can say your stable operation. Correct. Hence, we can say drive is a steady state stable point at the point A. Okay. Any confusion in this diagram? There is a stable operation. If you understood this stable operation, then you can easily easily find out the remaining graph, that is a B, C, and D. Any confusion in the stable operation point A? Yes, student. Any confusion? Okay. Because you have to just remember this T equal to TL, then it is a stable. Suppose T equal to TL is not equal, then you can say our given point is unstable. Okay. So now we can see unstable operation. Okay. Now we can see the unstable operation. Okay. So this not point A, this is a B. Okay. So it's figure 8, that is a B point. Point B is also stable. So you can see this is a load torque and this is a motor torque. So suppose you can give the just variation delta omega, then you will get also stable. Okay. Now we can discuss the detail about the point C, that is unstable. Figure number 9. Okay. So you can decrease in the load torque and you can decrease in the motor torque. Okay. Otherwise, you can see you can increase in the motor torque and you can increase in the load torque, and you can give the delta omega m. Then you can see this condition T is equal to TL is not satisfied. Okay. If T equal to TL is not satisfied, then we can say point number C is a unstable. Okay. Similarly, for the point figure number 10, load torque versus the motor torque. Point D, suppose you give the small variation here, that is a delta omega m. Then again, T is equal to TL is not satisfied. Okay, then we can say motor is unstable at point number D. Okay, so we can say, yes, we can say let's now examine the equilibrium point B, that is a figure number 8, is obtained when the same motor drives another load. Okay, a decreasing in the speed caused the load torque to become the greater than the motor torque. So just we have to give the variation in the delta omega, that is a speed, and then we have to check that T is equal to TL is satisfied or no. Okay. If satisfied, then point B is stable. If not satisfied, then point B is unstable. Okay. But given figure and given characteristic, given nature of the load torque and motor torque is satisfied at the point B, then we can say it is stable operation. Okay. And yes, B is an unstable point of equilibrium. Reader may be the similar to examine the steady state stability for the point C and point D is the given in the figure 9 and 10. Okay, so that figure C and figure D, that is a unstable operation once you give the delta omega m variation. Okay, so from this nature of the characteristic of the T and TL, we can calculate the we can find out the steady state operation, otherwise the unstable operation of the motor drive. Okay. Yes. So now we have to check just a mathematical thing. Okay. So we know T equal to TL. Okay. So suppose it's unstable operation, yeah, stable operation. Okay. So we can say above discussion suggests that equilibrium point. Where equilibrium point? So equilibrium point means suppose this is a point is a stable, then we can say it is a equilibrium point for the load torque and the motor torque. Okay. Equilibrium point will be the stable when increase in the speed cause load torque to exceed the motor torque. Okay. That means when at equilibrium point following the condition is satisfied. Okay. So del dt by d omega m greater than dt upon d omega m. Okay. So whatever you will change in the speed with respect to torque, it means that is a dt load torque divided by d omega m greater than dt upon d omega m. Okay. Inequality of the equation number 10. So this is equation number 10, not 2.24. This is equation number 10. Can be derived in alternate approach. Let small perturbation, small variation in the speed in the speed delta omega m and small variation that is a delta omega m result in delta t and delta tl. Perturbation that is a t and tl respectively. Okay, suppose you will change omega m to delta omega m. Similarly, that load motor torque that is a delta t and load torque that is your delta tl. Okay, then form, so only one time form, not two time. Form T equal to TL plus J d omega m by dt, that is a fundamental torque equation. We can say T plus delta T plus TL plus delta TL, because we can give the small variation in the delta, small variation in the speed as well as the torque, plus J d omega by dt, that is a omega m small variation, plus delta omega m by dt. So we can say we can replace T equal to delta T, TL equal to delta TL, omega m is equal to delta omega m. Okay, in the fundamental torque equation. So we can write equation number 11. Okay, so once we have this equation, just then open the bracket. So we can say T plus delta T, TL plus delta TL, and J d omega by dt plus J delta omega m by dt. Any confusion in equation number 10 and 11? Any confusion? Because we have to check the steady state stability, so we can give the just small variation in the load torque, yeah, maybe the motor torque, yeah, maybe the speed, and then we can say now we have to check the stable point, maybe the any stable point, maybe the a b c d, yeah, any characteristic. Any confusion, student, in the equation number 10 and 11? Okay. Okay. Yeah. So last two slide. So now we can say the fundamental torque equation. So we can substitute, we can substitute the fundamental torque equation from the equation number 11, from this equation number 11. Okay. So this is your final equation. Sorry, this is your final equation. We can substitute the fundamental torque equation and rearranging equation number 11. So we will give j del omega by dt is equal to del t minus del tl. So we have to substitute this, we have to substitute this equation from equation number 11. So we will finally get j d omega by dt equal to del t minus del tl. For the small perturbation, the speed torque curve of the motor and load can be assumed the straight line. Okay, so we can say this is a straight line. Okay, so maybe the torque TL and maybe this is a motor torque. Okay, so we can say delta T is equal to del d by dt by d omega m into delta omega m, because we can give the small variation in the speed. Similarly, for the delta TL is equal to del T by omega m into delta omega m. Okay, equation number 13 and 14, where dt upon d omega m and dtl upon d omega m are respectively slope of the steady state, speed torque, and load torque at operating point under the consideration. Okay. So this is a simple, we can say, so this is your speed. So maybe variation from this point to speed, this point. Okay. So this is a delta omega m. This is a delta omega m. Okay. So we can say delta t upon d omega m into delta omega m. So this small perturbation, it will give the your stable operation. Okay. So finally, substitute equation number 13 and 14. So both equation, this 13 and 14, we can put in equation number 12. Okay. So delta t and delta TL we have to put here. Okay. So we have equation J delta, d del omega m divided by del t is equal to del t minus del TL. So now we have a value of del t and del TL. So we can say now we can put the value of del t and del TL into equation number 12. So we will get the final equation. Okay. So we will get the equation number 15. Equation number 15. Okay. So this is a first order linear differentiation equation. Yes, we can see this is a first order linear differentiation equation. If initial derivation in the speed at t equal to 0 be the del omega m 0, then solution of equation number 15 will be okay. So del omega m is equal to del omega m 0 exponential, because we can calculate the initial condition. Okay. So initial condition, we can say it is exponential condition. Okay. From the initial condition, we can calculate the delta omega m. How much variation we can give. Okay. So that delta omega m is equal to del omega m, that zero condition, exponentially minus 1 by j dtl by d omega minus dt upon d omega into t. So this is a simple equation calculated from the equation number 15. Okay. So equation number 16 from equation number 15. Okay. And we have to calculate the delta omega m. And why we have to calculate the delta omega m? Because we should know how much variation we have to give for the stable operation. Okay. So from equation number 16, we can say an operating point will be stable when delta omega m approach to 0 as t approach infinity. Okay. For this to happen, exponent in equation number 16 must be the negative. Okay. Then we can say your system is a steady state stability of your electrical drive. Okay. Yeah. So this is my last slide. If you have any confusion in this topic, that is a steady state stability of the drive, then please ask me. So most important condition, that is a T is equal to TL. And you have to give the variation, that is a delta omega m. And then you have to check is satisfied for the every delta omega m, then you can say it is a stable operation. If it is not satisfied, then you can say it is an unstable operation. So key point from the today's class, that is a time and energy losses of the transient operation and steady state stability of the electrical drives. So if you have any question, any difficult from today's class, then please let me know. Yes, any confusion, any query? Yes, student. Yes, Ashish, any query?
No, sir, but that can you teach us that RK method, sir? Actually, I did not learn that in BTech also and not in power system also.
So Rangakutta method is not important for this subject now. I mentioned the Rangakutta method here because of the maybe the any other subject. But in this subject, Rangakutta method is not important. But I
Yes, sir,
will
but
teach
sometimes
you. Yeah.
we have to do solve that non-linear equation also. We have to encounter that also,
Yeah.
because I
So
think
I
if you
will
not
teach
teach
you.
then
Yes. Yeah, I got it. So once I have a time, so first I have to complete the syllabus. So once we have a remaining time, then I will again cover this Rangakutta method. But this time I am sorry because we have already the lagging in the syllabus. So suppose I have a time, then I will cover this Rangakutta method, because this Rangakutta method is important for the power system analysis, and there is a stability analysis in the power system. So is it okay for you?
Okay, sir. Okay.
Yes, sir. Yeah, because suppose I have a time, then I will cover this Rangakuta method. So suppose I will complete the syllabus before the time duration. Okay. Otherwise, I will take any extra time slot. Maybe once I will visit in the Nepal, then maybe I will teach in the physical mode. Okay. Then is good, but not in the online class. Okay. Because Rangakutta method is a totally mathematical step, and mathematical step maybe I will explain the online, then it is not good to the understand. So just remind me once I will reach in the Nepal, then I will teach you the Rangakutta method. Okay. Okay, is it okay, Asis?
Okay, sir.
Okay. So so we completed the first unit, that is an introduction to electrical drives, and we covered the many topic, that is a fundamental of electrical drives, fundamental torque equation, fault coordinate operation, and the components of the load torque, classification for load torque, and how to calculate the time and energy losses in the transient operation, and finally we discussed the steady state stability of the electrical drives. So that is only the first unit. Okay. And from the next class, we will discuss the introduction of the control of the electrical drives. So that is a fundamental concept of the electrical drives. So how we can control the electric drives. Then mode of the operation of the electrical drives, and speed control and drive classification, and the closed loop control of the drives. Okay. So before starting of this topic, I will cover the power electronics converter. Power electronics converter. All of you know about the power electronics converter. There is a AC to DC converter, DC to DC converter, AC to AC converter. Okay. And DC to DC converter. Okay. Rectifier, inverter, chopper, and cyclo converter. I think all of you know about this converter, correct? So I will spend around 30 to 40 minutes on the converter part, and that is a second unit. Okay. And then we will start this topic, and that is your third unit. Okay. So in the next class, I will cover the fundamental of the power electronics converter. There is a rectifier, inverter, chopper, and cyclo converter. Then we will start with the how we can use this power electronics converter in the electric drives, and how we can control this power electronics converter through control algorithm. Okay. So if you forget this concept, that is a power electronics converter, then please revise your concept. Okay. Then you will easily get the idea how we can control the drives. Okay. Otherwise, it will difficult to understand the drive concept, how we can controlling the power electronics converter, how we can operate the switch, and how we can give the pulses to the semiconductor switch. Okay. So if you remember this concept, then it's a very good. But if you forget this concept, then please revise it. Okay. Done. So this is for the next class. And one more thing I would like to know. So your class time will change, or no? So any idea? So Jitendra sir communicate with you. So any idea? So your class maybe the from the Thursday to it is shifted to Friday. Any idea?
Yes, sir. Jitendra sir told that you will shift class from Thursday to Friday.
So for the both faculty,
Um,
correct? For the Bharat sir as well as the Maya class, correct?
yes, sir. Yes, both.
Okay. So that is a great. So next class on the Friday. Okay. That is the
Yes, sir.
same time after the Bharat sir class. Okay.
Okay, sir. Bye bye.
Okay, thank you so much. Bye bye.